where is this one? Okay, so let us go to the continuation of the lecture, but I will skip these ones. I have written all the proofs in the notes. So, but because they are very easy for you from the calculus, I want to just skip them. So this means that if I know that the limits of two functions exist, one of them f is L, the other one is m. So if you add them, the limits will be added. If you multiply them, the limits will be multiplied. And if you divide them, provided that the denominator is not 0, the limits will be divided. Yeah, of course, I would recommend you, if you're interested, to look at the proofs. Okay, the next one is a squeeze theorem, which probably is very familiar to you from the calculus if you have a function, but this one cannot be in any metric space. So you see here, A is a subset of any metric space, but the domain, the codomain should be the set of real numbers. Can you tell me why? By the structure of the theorem. Do you know why on the right-hand side I have to have R or some versions of numbers? Because you know that in metric spaces there is no guarantee that the elements are numbers. But the codomain, if the squeeze theorem is supposed to make sense, the codomain should be a set of numbers. By the way, I should also mention in the previous one. Can you tell me why in the previous one the codomain is R? You see, the domain is still a subset of a generic metric space. But why the codomain should be R? Yes?
Because what does it mean to, I assume it's because what does it mean to add?
Exactly.
If you don't
we do not have the
numbers?
notion of addition in a generic metric space. We have just a set of points that we can measure the distances. But we cannot add the points in a generic metric space. There is no addition defined there. So if I insist to add, then I have to work with numbers, okay? Or I have to work with groups in an abstract sense. But we have to define a binary operation there. Is that right? So we have to impose some structure on that. Okay, why do you think this is the case for the squeeze theorem as well? Why? Yes?
Because even though there is such a thing as distance, I feel like saying that something is less than other things.
Yeah, the order, we don't know. We don't have the order.
No.
We cannot order them. We cannot say one element in a generic metric space is less than or equal to the another element. So the notion of order is important for this theorem. So that is important from conceptual point of view. You understand that the codomain should be a set of numbers or any set in which we somehow come up with the notion of order. Okay, there are abstract setups for that as well. Okay, so now let us go to this one. The content is clear. If a function is sandwiched between two functions and the functions on the left and the right have limits, the middle one has the limit and the limit is the same. That's the meaning of the squeezing theorem. Okay, now we want to talk about the most important concept here. That's the continuity at a point. Okay, so let us start with this. 911. It's a very bad number, yes. So we have to be careful. So continuity at the point in metric space. If I have two y dy, I have two metric spaces. I want to talk about, and then I have, of course, a subset A of my, the same setup as for limits. And then I have a function from A to y, and then I have a point P, this time in A, not in the A part, not in the limit set. Okay, so I have this setup. I can say that F is said to be continuous at P if this happens. For every epsilon greater than 0, you can find a delta greater than 0 such that for all x, if x belongs to A, and dx of x and P is less than delta, these two imply that the distance between, do you remember what was the continuity in calculus? How did you learn the continuity in calculus? the limit of f of x when x goes to p is equal to, we say that f is continuous if the limit value is equal to the value of the function itself. So it becomes f of, do you remember that? That was the definition that you learned in elementary calculus. Okay? So now that is more or less the generalization of the same concept. So can you complete it for me? Yes?
The distance of x of f of x comma f
Yes.
of p is less than x.
Exactly, but on the y side, yes?
Yeah, of course.
That's the definition in a generic metric system. Okay, and then you see a little bit of differences. So this is not exactly that one, because for this one to make sense, P should be a limit point. But I am not asking P to be a limit point. So the notion of continuity can also make sense if P is not a limit point. This is why I do not define it in that way for you. I define it in this way. The second difference is that, do you see what is the difference? Another difference? So of course, in my case, I had Q. In the limit case, I had Q. But for continuity, this Q is exactly the value of the function at the point. So this is not Q. The second difference is that we had this 0 in the limit form, but here I do not have it. And the third one is that I am not restricting myself to the limit points only. I am asking that P can be any point in the A. This one that I do not exclude it is meaningful, because when I talk about continuity, it means that the values of the function at that point are getting close to the value of the function itself. So it means that, okay, there is no reason that I exclude x. Because you know that, by the way, if this is 0, x and p are the same, so it is vacuously true. Because if I choose x to be p, f of x becomes equal to f of p, and the distance becomes 0, and 0 is always less than any positive number. So regardless of what happens, this is vacuously true, because the right-hand side will always be true. Is that right? So we don't do that. So just remember this definition. But now, one thing that I want you to understand is that P belongs to A, there are two possibilities. And both possibilities are acceptable. But this is a little bit delicate, I want you to understand. When I say P belongs to A, there are two possibilities. Either P is a limit point or is not a limit point. Okay, what was the name of this one? If P belongs to A, but it was not a limit point, what was it called?
Interior.
What?
Isolated.
Isolated. So this means P is isolated. Okay, so what I want you to understand is that if P is an isolated point of your domain, the function is automatically continuous there. Okay, so can you tell me why? If P does not belong to A prime and belongs to the set, P is an isolated point. Yeah?
Is it because that's the only point and it's included in the set, so there's nothing else there? It's just like that.
No, it is exactly as we did before. Do you remember how I translated this in the language of neighborhoods? So here, this means that X belongs, but here I do not have that set excluded. So this means that X belongs to the neighborhood of P with radius delta intersect A. Okay? So if P is an isolated point, then it means that there exists a delta for which this one is only P. Yes? And in that case, this is also valid. So this means that if P is an isolated point, you can always find delta so that it works, and it means that my function is continuous at isolated points. Okay? So remember, this is a very nice fact. Okay? So if I am working with a function and I pick an isolated point from my domain, it's a little bit counterintuitive with what you have learned in calculus, because if a point is isolated, more or less it means that on the left side and on the right side there is no functions up there. Yes? But still, we want to say it is continuous because of this definition. I want you to go, and of course, I have written this remark here for you. Yes, this remark, the differences I described, so that is this one. So let me read it for you. So unlike the definition of limit, the definition of continuity at a point does not require P to be a limit point of A. In fact, if P is an isolated point of A, then every function f from A to y is automatically continuous at P. Indeed, if P is isolated in A, that is the meaning. There exists some delta positive that the only point of A satisfying dx x and P less than delta is P itself. Therefore, for any epsilon greater than 0, the same delta works. That's exactly what we described, yes? So this is a little bit, you see, this definition, the calculus definition, is not completely identical with this a little bit more advanced definition, yes? We cannot even talk about the continuity of the functions at isolated point of the domain, because you cannot probably approach to those points, yes? If that point is an isolated point, can I talk about the limit? No, because you remember the notion of limit, when I write this symbol, automatically I am assuming that P belongs to A prime. Okay? So these two definitions are not 100% equivalent, but they have some relations to one another. It's not that far away. I want you to understand. So that's one thing that you have to understand. Okay, so this one is also something you already know, even in calculus. So you know continuity is a local concept. I can talk about continuity at a point, which means this. So what does it mean to talk about continuity? If I say my function is continuous, in principle something is missing because continuity should be described at one single point. When I say my function is continuous, what do I mean by that? Because whenever the notion of continuity comes to mind, you need to ask continuity at which point? Because the function could be continuous at a point without being continuous at another point. Okay? So when I say my function is continuous, what do I mean by that then?
All the points.
All the points. It means my function is continuous at all its domain points. Okay? Or if I want to say that my function is continuous on a set, it means that whatever point you choose from your set, your function is continuous on the point of that set. That's the meaning. So this means that it's a global meaning of continuity then. Okay, but then as I told you before, this is not extremely unreasonable to have this equivalency, continuity and limits. So I have two metric spaces, and A is a subset of X, and that's the same setup, but this time be careful, P belongs to A, be a limit point again. When P is a limit point, the continuity that you learned today and the continuity that you learned in the calculus are equivalent. Okay? So this is the theorem. I think you can see that. So let me just do 9.15 together. Do you understand what is going on? So here I have again my setup. I have two different metric spaces, and then I have a subset of X. And this time I have also a function from A to Y, but P belongs to A prime. You see here, P, in my original definition for continuity, I don't insist P belongs to A. But for this theorem, I insist P belongs to A prime itself. If that is the case, continuity at P and the one you learned in calculus are equivalent. So I would say that limit of f of x, x goes to P, is equal to f of P if and only if f is continuous at P. So in this course, if you want to use this for continuity, you have to be only careful about one thing. If the point is a limit point of my set. If that is it, if you're more comfortable, you can use it. Okay, the proof is extremely simple because you know that the definition of continuity is very, very similar to the definition of this one. The only difference is that you don't have that greater than 0 part. But for that one, it does not impose anything because in that case, I have 0 less than epsilon if that is. So it is very easy to prove. I don't want to prove it. It's just a matter of explanations, one line. Okay, but now let us go to something similar for that theorem that we had for limits. I will not prove this one as well because they are a combination of them, but it is important to know this. But there is a very nice example that I want to describe it for you after coming this one. So do you see that? Could you somehow expect this theorem? Can you read it yourself? So let me read it together. Let us read it together. We have again the same setup, two metric spaces, and then I have a subset of x, and I have a function. But P is a point of A. We want to prove that if you say f is continuous at P, it is the same thing as if you say for every sequence Pn in A, if Pn goes to P, f of Pn goes to f of P. Do you agree? This is very similar to the limit part. Okay, I hope that you see that the proof shouldn't be hard. And I hope that you could do it yourself. But do you understand what does it mean? So from now on, if I want to prove that a function is continuous at a point, I can use this epsilon delta definition. If I know the point I am talking is a limit point, I can use the calculus definition. But there is a third one which is very important in this course, and this is the consequence of this theorem. So this theorem tells you that if you want to prove that a function is continuous, if you want to show that a function, let me put this one here, this inside. If I want to show that my function, which is from a to y, is continuous at this point, one thing that I can do is now to do this. I imagine a sequence that goes to P, okay? And then I prove that the sequence of the values goes to f of P, okay? So because if this P is here, f of P will be here. And if I have a sequence that converges to P, for example, Pn, this Pn will give me a point here in the codomain space f of Pn. So it means that if I have a sequence approaching to P, I will have a sequence here. So if I want to prove that my function is continuous at this point, I should prove you, one way to prove this is to prove that every sequence in A that takes me to P will actually have a sequence, a counterpart sequence that takes me to f of P, the sequence of values. So that's another alternative way to prove that a function is continuous at a point. Is that clear? Again, this theorem is useful if you want to prove that a function is not continuous. Can you tell me what the strategy will be? Because it is very similar to the one we had. If I want to prove that my function is continuous at a point, I have to convince myself, no matter which sequence I choose that approaches to P, the sequence of values will approach to f of P. If I can do that, then it means that I have shown you that the sequence is, the function is continuous. Now, if I want to show that, no, the sequence is not, the function is not continuous at P, what would be a good strategy?
Find one more that isn't the case. Or
This is one way. Find one sequence, that's very good by the way. Find one sequence that approaches to P, but the sequence of values diverges. This is one way. But another way. Again, exactly as before for functions. If I get two sequences that approach to P, but the sequences of values approaches to two different values, again, the function is not continuous. So we have two alternatives. Thank you very much. By the way, that method will also work in the other case. I didn't mention that there. Yes? So if you find a sequence that converges, but the sequence of values does not converge, so it means that the limit does not exist as well. Okay? Is that clear? Okay. So now let us go to this very famous example. This is called Dirichlet function. This Dirichlet function takes two values, either 1 or 0. If you input a rational number, it gives you, if you, oh, so I was thinking how much time we have, so it's not working. Okay. So if you give a rational number to Dirichlet function, it gives you 1 back. If you give an irrational number to Dirichlet function, it gives you 0. So somehow it jumps up and down between 0 and 1, but because they are dense, so the number of jumps is actually infinitely, as you can imagine it, but you cannot draw it, okay? We want to show that f is not continuous at any point of R. So this is one of those nice functions, because when I ask you imagine a function that is not continuous at even one single point, might be it is not that easy to come up, because when you want to draw something, as soon as you just draw something like this, it is continuous at infinitely many points suddenly. Yes? Okay, so it means that coming up with this is not that easy, but of course we want to go through it to see why it is not continuous at even one single point. Okay, so let us try to do it carefully here, because this is one of the important examples. So the function, let me write it like this. F of x is equal to 1 if x belongs to Q. So 0, instead of writing that cumbersome notation, let me just write something like that. It doesn't belong to Q. We want to show that this function is not continuous. It turns out that for technicalities, I have to divide the problem into two pieces. I have to show you that this function is not continuous at any rational number. Then I will show you that this function is not continuous at any irrational number. Then what does it mean? It means it is not continuous at any point. Yes? The rational ones, I think you can immediately come up with the solution yourself. Okay? So, we consider two cases. Case 1. Let P be in Q. We show that F is not continuous at P. Okay, so how can I do that? You need to come up with two sequences that converges to this P, any arbitrary rational number, but the sequence of values don't converge to the same point, or as you told, find one sequence that converges to P, but the sequence of values diverges. Can you come up with a sequence? Okay, so it needs a little bit of experience, but it is not hard. I define for you my sequence to be this P that you gave me plus the same technique, 1 over n. Okay, first of all, do you agree that this is a sequence in Q? Why? Because P from the beginning was a rational number, and 1 over n is always a rational number. So when I add them, it is a rational number. Yes? So Qn is a sequence of rational numbers, of rationals that approaches to P. Yes? Okay, so what I am saying is that Qn approaches to P. Okay, now let us look at the sequence of values. So what does it mean? It means that I calculate the sequence of values. What happens? This becomes f of p plus 1 over n. Tell me what the answer is. F is the Dirichlet function. I am feeding it with p plus 1 over n. P, by my assumption, is rational. 1 over n is rational, so the sum is rational. So what's the output? 1. So it means that even though the sequence is not constant, but the sequence of values are all equal to 1. So it approaches to 1, because all of them are constant. Okay, can you come up with something else now? So I want to define another sequence for you. But if I want to do it so that it works, what is your intuition? What type of sequence I should construct so it works? Yes, a sequence where?
In R without Q.
Yes, in the set of rationals. And can you come up with that yourself? No, it is extremely simple. So give me a sequence in the set of irrational numbers so that it again converges to the same rational p. Yes?
P plus pi over n.
Pi over n. I was thinking about this one. That's also correct. Pi over n is also correct. So why is that true? Do you think that this is irrational?
Yes.
Why? Because 1 over n is rational. When you multiply it by an irrational, it is not hard to prove. The result is irrational. And if you have irrational added to a rational, again, it is not hard to prove that the result is irrational. Okay, so it is irrational. Am I respecting the rules? Yes. Because if I ask you where this converges to, you will still tell me it converges to P. But now let us calculate the sequence of values. Can you tell me what the answer is? 0 this time, because all of them are irrational. Yes? And this will approach to 0. And they are not the same. So this means my sequence is not, my function is not continuous at any rational point that you pick, no matter which one you pick. Yes? But it is not finished yet because I want to show it is not continuous at any point. I showed you this is not continuous at any rational points. So the number 2, I will write it down because I want to continue. So I want to continue, but I want to have the same strategy. This time I would say let P does not belong to P. And I want to show that, we show that F is not continuous at P. Okay? I want to do the same strategy, but this time you have to know a little bit more. So, can you come up with the first one? This one is not rational. So what do you think I will do? This time, let me write it as A sub n. I define it P plus 1 over n. Okay? Is this rational or irrational now? It is irrational because this one is irrational, this one is rational, so the sum is irrational. So then this means that an goes to p, so that's good. But let us look at the values. But what happens this time?
It's 0.
It is 0. And it goes to 0. But the other one, you have to be creative. I did it in one of my previous lectures for square root of 2. I don't want to do it now for you, but the other, for example, if I want to define the second one is this one. P 10 to power n, P floor divided by 10 to power n. Okay? This is extremely simple using a squeezing theorem. I have written it in my notes. So if you want to prove that this one, first of all, do you agree this is rational? Because even though this is irrational, but when I multiply it by a power of 10 and take the floor, it becomes it becomes an integer and divided by another integer. So that's the only thing that I am trying to sell to you, and you have to convince yourself this will approach to P. It's extremely simple, it's not hard. Okay, so you multiply them. So let me just do that. So if I want to prove that that's the case, that's a good practice for a squeezing theorem as well. My claim is that this is going to P. Why is that? So I would say that the floor of 10 to power n P divided by 10 to power n, I called it Bn. Yes, so what does it mean? It means this one times that. This means that the floor is equal to 10 to power n B. Yes? But do you agree that this, because the floor of this number is this number, it means that this number is sandwiched between minimally this number and maximally, which cannot even reach to that one more. That's the meaning of floor, yes? If you have a floor of number equals to a number, it means the number itself is sandwiched between that number and 1 unit more. Okay? That's the meaning of a floor. And then I divide everything by 10 to power n. So what happens? This becomes B less than or equal to P less than or equal to B plus 1 over 10 to power n. Yes? And now what I will do, I will add minus P to all sides. So this becomes 0. This becomes P minus, no, sorry, this is not B. This is Bn. This is Bn. Sorry. Yes. So I subtract minus Bn. So this becomes P minus Bn is less than 1 over 10 to power. Do you agree with this? Okay, can you finish the proof now? My claim is that this a little bit weird sequence, first of all, it's a sequence of the rational numbers. You agree with that because integer divided by integer. And then I'm claiming that this approaches to P and this is the proof. It's not finished yet, but there is one more step. Can you complete it for me? I want to send n to infinity. The limit of this side when n goes to infinity is what? The limit of this side is 0. So by the sandwich theorem, the limit of the middle one is also 0. So this means that the limit of P minus Bn is equal to 0. So this means that the limit of Bn is actually P. Yes? Yeah. Because that's a constant. Okay, so that's exactly what I wanted to show. I wanted to show that Bn approaches to P. And then everything is done. Do you agree? Because now I know that Bn approaches to P. Yes. And then this implies that f of Bn will be what? 1. Because it's rational. And it approaches to 1. Okay? Am I in trouble? No. Because the other one approaches to 0. This one approaches to 1. And they are not equal. So this means that the Dirichlet function is not even continuous at irrational numbers. So it is not continuous anywhere. So this jumping up and down is so rapid that you cannot even draw one line, short line segment. Because if I can draw that, by the way, in how many points it is continuous? Infinitely. But this one is not continuous even at single point. It's a very nice example. Okay? So the one that I have written in the note is a little bit different. But then in the boss, I was thinking about that maybe this is a better approach. So you can also read that one in the notes. Okay, so let us now go to the next one. This is an extremely important theorem.
Why do
Yes.
we get a strictly less than after we subtract Bn in the last step?
This one?
Yeah.
Because this one is a strict.
Okay, but in the step before we have...
No, you are right. Yes, thank you very much. Thank you. But by the way, you know that from this one, I can always conclude this one. Because if A is less than B, definitely is less than or equal to B. But the other way around is not correct. So if I go forward and write this one is equal, it's not wrong. Yes? But let us stick with that. Okay, so there is one theorem. So I have to move the other ones to the next lecture. So I will remove it from the notes and put it for the next one. But this is an extremely important characterization of continuity. It is topological characterization of continuity. So this is something I want you to know as well. Okay, so let me explain what does it mean here and try to justify it as much as we have time. But at least understanding it is extremely important. So if you have the same setup, so theorem 918, if I have the same setup, I have two metric spaces, and then I have a subset of, no, I have written, by the way, let us write the function from x to y this time. These two are equivalent. One, f is continuous on x, not at one single point, on the x in its totality. Number two, for every subset V of y which is open, the inverse image of V is open in X. This is topological characterization of continuity. Or a metric space setup, which is completely independent from epsilon delta definition or something like that. So what does it mean? It means that if I have a function from this metric space to another metric space, f, if I want to show that f is continuous everywhere, not just one point, everywhere. If I want to show that my function is completely continuous on its domain, one way I can do is to show that if I choose any open subset V from Y and pull it back. Do you remember this? We had the first lesson of analysis, the inverse image. The inverse image will be the points that are mapped to V under F. That is called F inverse of V. We had it in the first lesson of analysis. So it means that if I do that, so if I choose any open subset of Y and I pull it back, means by inverse image, then this becomes open in X. So if the inverse image of every open subset in Y is an open subset of X, then my function is continuous on its domain, and vice versa. If f is continuous on its domain, then this inverse image of every open subset of Y is an open subset of X. Okay? So we have 5 minutes. Let us try to at least prove one of them. Okay? Which one is better to do? Okay, so let us go from 2 to 1. Okay. Okay, I take this for granted, and I want to show that f is continuous on x. So how should I show that? If I want to show that f is continuous on x, I have to show that f is continuous at every point on x. So I would say let p belongs to x. We show that f is continuous at p. Okay? But if I want to show that f is continuous at p, I have one thing in my head, that's the definition. So I would say let epsilon greater than 0 be given. We prove that there exists a delta greater than 0 such that what happens? for all x in x if dx of x and p is less than delta. This implies that dy f of x and f of p is less than epsilon. This is what we want to prove. Yes, we prove this happens. Okay, so let us have a picture here. So what do I have here? This is x, this is y. I have picked one random point from my set. I want to show that my set, my function is continuous at this point. It means that epsilon is given to me. So here is f of p. I already have my epsilon around it. Yes. And I want to show that I can fine-tune my delta around p so that this is mapped here inside. So what do I do you think, with this? I would say that the neighborhood centered at p, f of p, with radius epsilon is a subset of y. Do you agree? Yes. And then it is open. Yes? So you see what I am doing? My goal is to convince you that there is a delta with this property. Okay? But do you remember this means f of x belongs to the neighborhood centered at fp with radius epsilon. Okay? We want to prove that. We want to find this delta so that it works. But what I'm saying is that you gave me the epsilon. I go to fp and find the neighborhood around that by the radius epsilon. This becomes a neighborhood of that, and you already know all neighborhoods are open. And now what I know is that if I have an open set here, the inverse image will be open here. Yes? So this means that by number 2, this means that the inverse image of n of f of p with radius epsilon is open in x. Yes? Do you agree? Okay. So then what does it mean? When you say that this is open in x, it means that, first of all, do you agree that this set contains p?
Yes.
Why? Because fp is one of the points of this neighborhood. When I pull back, when I find the inverse image, it means that I am looking for all points that are mapped here. One of them is p. So definitely p belongs to this. Okay? So, on the other hand, we know that p belongs to that. Yes? We also know that this is open. What does it mean? It means there exists a delta such that the neighborhood of p with this radius delta is a subset of the open set. Is that right? Because when you say that a point is in the open set, it means it is an interior point. It means there exists a delta for which then delta of p is this one. And now, because we don't have time, so you just need to prove yourself that this delta is your claim delta. Okay? So I hope that you have learned this gymnastic of delta and epsilon, yes? So you somehow, it's very natural, by the way, it's not very hard. So it's very, very intuitive what you're supposed to do. But you have to go and study it a little bit carefully yourself and then do the other way around yourself. Any questions? Okay, so I will take the rest of this from these notes. And then, of course, thank you very much.